everyone, and welcome to TLV's seminar on water hammer and steam and condensate systems part 2. Today we're going to go steam-induced hammer, and we're going to cover flashing condensate hammer in condensate return lines and vertical transport lines. So I'm going to have several collaborators with me, and they're going to be able to answer the questions. The first is Norm White, our Executive Vice President.
Good afternoon, everyone.
And John Walter, our Business Development Manager, but formerly the International Consulting and Engineering Services Manager.
Good afternoon, everyone.
And Andrew Moore, the Consulting and Engineering Services Manager for TLV Corporation.
Hello.
And Justin McFarland, the Engineering Manager for TLV Corporation.
Hello, good afternoon.
Thanks, guys. All right, we'll get started. But first of all, I'd like to ask you to take a look at the disclaimer. We're going to turn our cameras off so that you can see the screen. What we're going to be giving today are tips based on our experience. But even though your application may look the same, usually every application is unique. So this disclaimer is just to advise you to make sure that everyone understands it's just tips. If you want us to review an individual application, we're more than happy to do that and make a recommendation for your unique application. Other than that, this is just a guideline today. So please take a few seconds to read that. Okay, thank you. So what we're talking about is mitigating risk. So if you're familiar with API 580 and 581, you're familiar with this risk assessment matrix. What we basically want to do if we take a look at different assets is we want to take a look and see how we can reduce or mitigate the risk of those assets. We cannot change the consequence of failure unless we change the system design, but we can, however, reduce the probability of failure and drive it down by taking proactive actions to mitigate risk. If you want to learn a little more about that, please read Dr. Brian Kane's article in Inspectioneering Journal. You can also find it on tlv.com. He is an asset integrity specialist at TLV. All right, so we take a look at hammer and systems. There you see hammer and steam systems. We covered that in the last session, part 1. Hammer at equipment was also covered a lot in part 1. And today we're going to focus on hammer in the condensate recovery system. So you can measure hammer in the return system or the steam system with a sonic camera. Here's a photograph of a perfectly nice system. And then there you see the hammer with the sonic camera. And now you see there again, no hammer. Take a look at the timestamps. You can see that these timestamps are only 4/100ths of a second difference. That's how quickly hammer can come and dissipate. So today we're going to talk about water hammer and condensate returns, the cause and mitigation. Well, you know these implications. I'll let you read them at the top right. There are others, but those are certainly some important ones. We don't like to see blowouts like this. It's a safety consequence, lost condensate, repair cost. You can take a look at the economics of condensate recovery by going to TLV's toolbox, which is for your iPhone or Android phone, or you can go to tlv.com and take a look at engineering calculator and put some data in, and it'll come up and tell you the energy value, the water and chemicals value, the effluent treatment value. But what I like most about condensate recovery is I want to reduce the boiler steam that's diverted to makeup. You really want boiler steam to go out to your production plant at the highest pressure possible. Why? Because you get the highest temperature, and that drives the most heat into your process by having the greatest temperature difference. If we're diverting a lot of steam to makeup, sometimes it actually reduces our boiler pressure and our temperature that's delivered to the site, particularly under rainy days, and that reduces our production value. So we want to capture, condensate as much as we can. So let's take a look at condensate return systems. There's 3 types. There's a 2-phase system, which is non-flashing. That means the condensate is traveling in the same pressure. This is basically the steam and condensate that's traveling to a steam trap from a piece of equipment. There's flashing. This is when condensate travels to a lower pressure due to a positive pressure differential. This is when the condensate exits a steam trap or some other drainage device and goes to a lower pressure system. But it starts off as condensate and then it ends up on the other side as condensate and flash steam. And there is a single type of condensate return system. Okay, that is when you have a pumped return normally. Let's take a look at what that looks like. Simple graphic, there's a non-flashing part. It's condensate that exits the equipment. It goes to the steam trap. It's non-flashing, but it is two-phase. It's condensate and liquid in a liquid form and also steam. The trap traps the steam, and then it's going to discharge condensate downstream, but that'll be high temperature condensate, so it'll be flashing. It'll have liquid phase and it'll have also a vapor phase of the flash steam. And then we'll put that into the vented collection tank, and from that we'll flash it off, and we'll take pumped condensate as a solid liquid phase outside of that tank and push it back to the boiler or another transfer pump. This is the simplest system. It's the lowest cost. It's just a steam trap to get it over to the vented collection tank. There's no other pumps involved. It's the most reliable system. There's no special equipment, and it's easy to implement. But it doesn't work that way most of the time, because a lot of times traps have to go against a higher back pressure, which means there's a negative return. They can't get it all the way back to that boiler or to that other transfer pump. So when they're pumping against a high back pressure, how do we calculate the back pressure? Well, we say total dynamic head. That's three components. It's the vertical lift into the return header, or to the flash vessel, or both. It's the piping frictional loss along the way, and it's the destination vessel pressure. Sometimes the flash drum, knockout drum, flash vessel, they have a positive pressure because they're doing flash recovery. So we've got to add those three components up. That's the TDH. People just say the back pressure. So here we've got the non-flashing portion, and here we've got a flashing portion, but the steam trap on the inlet side didn't have enough positive pressure to get it all the way down a long distance. So it's got to go to this vented receiver, and we're going to put some sort of a pump in there, whether it's a power trap system or a other type of pumping system. And we're going to pump that, as you see in the pump line. So we'll have flashing condensate before the pump. We'll vent off the flash at the receiver, and then we'll pump the liquid phase downstream. Well, we might be pumping that a rather long distance. So when we are, commonly it's going into a main collection tank. There could be some risers in there, a lot of risers in there. And then we'll have another pumped return going to the boiler. This long distance is where we can see a lot of trouble sometimes with condensate returns, and we're going to take a look at that further today. Right now, we're going to take it along a long delivery line, and you have a high velocity discharge coming out of the pump. You see the broken line to symbolize that it's a long return. It's not just a simple return. And when you've got a pumped single phase line with a long return, you can get back slams. So what you do for something like that is a lot of times you can mitigate that by putting a vacuum breaker and a liquid air vent to mitigate that. The vacuum breaker is right at the riser there, and that prevents the suction from pulling back and creating a back slam by bringing back, breaking the vacuum in the system. And then the air vent is at the end of the long run, and that gets rid of the air that came into the system to break the vacuum. Okay, so this is interesting. There's three types of water hammer. CWH, I never heard of that, and SWH and CIW. Oh, I know what CIWH is. Everybody seems to know that, but I'm not so sure that everybody has it exactly the way, I want to talk about it. In a steam line, you can have condensate-induced hammer. You know that. That's when you've got a steam line and a water slug closes off the cross section. All water hammer is created by what? It's created by water. But we have to know exactly how the water is creating the water hammer to know how to deal with it. So in this case, it's rather simple. It's a water slug, but what is this one called steam condensation-induced water hammer? What? Well, that's in a steam line when steam collapses. So they're both red, so they both occur in a steam line. And this one is blue, so that means it occurs in a condensate line, and that's called steam-induced water hammer. That's when a condensate line has steam collapse. Wait a minute, the one above it has steam collapsing, and the one beneath it in the middle has steam collapsing. What is that? Let's take a look at these again. Condensate-induced water hammer. We have a water slug that runs down the pipe, closes off the cross section, gets propelled by steam, and it makes a big bang. Why do we have this fancy name, condensate-induced? Why don't we just call it slug hammer? That's what it is. It's a slug hitting a vertical riser usually, unless it hits a closed off valve. Now we've got red again, which is a steam line again. This is condensation-induced water hammer. It's really when the steam condenses so rapidly that it collapses. It happens in a steam line. When does it happen in a steam line? Well, usually two types of situations. The steam line was flooded, and then steam is injected into a flooded line that shouldn't be full of water, but it's full of water. And steam comes into that. There's so much water there, it's a heat sink, and it collapses the steam. The other way is if you've got a steam line underground, like in a tunnel or in a vault or in a pit, and you get a flash flood, and all of a sudden the rising water table goes over that steam line, and it condenses the steam so rapidly, it's a rapid condensation event, and it collapses the steam. Why do we call that condensation-induced or steam condensation-induced? Why don't we just simply call that collapse hammer in a steam line? Isn't that a lot easier to say slug hammer in a steam line? Now you know it's coming from a slug. And collapse hammer in a steam line, now you know it's coming from a collapse of a pocket. And now when we go to condensate line, well, water isn't going to collapse. So what's going to collapse and create hammer? Well, it's going to be a steam pocket that collapses. So that is collapse hammer, but it's collapse hammer in a condensate line. So now you've got basically three types of simple hammer to remember. Slug hammer in a steam line, collapse hammer in a steam line, which tells you a pocket's collapsing, a steam pocket's collapsing. And in the condensate line, you have collapse hammer. That's when a steam pocket is also collapsing. We're going to take a look at this today. So here we've got a line that's got some steam in it, it's got some condensate in it. Steam leaks form pockets. The pockets can collapse. Now take a look at this animation at the bottom right and watch the pocket collapse. There's the wave. You see the pocket collapse. Boom, there's your hammer. Let me watch that again. So there's a pocket. It could be live steam, could be flash steam. There's a lot of water around it. All of a sudden the pocket collapses. Another hammer event. So when steam displaces water, creating a void, that doesn't have a lot of energy because it's usually not a lot of massive steam. The pockets form, and when the pockets collapse, it creates a shock. In a vertical line, think about this. If you've got a vertical line that's feeding up 20, 30, 40 feet into a header overhead, think about the head pressure from that water column on that pocket. That is already compressing the steam, and when that pocket collapses, you get more rapid acceleration to close the void. People often say to me, why is it you don't like the so-called cascade systems where you take the condensate out of a high pressure system like 600 psi 42 bar, and you discharge that condensate into a medium pressure steam line, like at 150 pounds pressure, 10 bar. Well, I hate that because that 150 pound 10 bar pressure is exerting a back pressure on this pocket. So now you not only have the 30, 40 foot of riser that's exerting a pressure on it, but you've got the 150 10 bar steam pressure pushing on that. When that pocket collapses, you're going to have a rather violent bang from the high acceleration. For those of you that have never seen this video before, I hope that you enjoy it. This is a steam-induced hammer event. Why? Because we're talking about condensate lines. This could be a steam line that's flooded with water on startup because the water was never drained out. But for the purpose of this discussion, it is a condensate line, and it's flooded with condensate, and we're going to put steam into it at low pressure, around 5 psi pressure. What is that? 0.3, 0.4 bar, somewhere around there. And we're going to put steam into it and watch how quickly it dissipates because the water is a huge heat sink. Here we go. Get ready. I'm going to let you just watch that for a few seconds. Can you imagine how rapidly that is collapsing? Look at that pocket of steam. Just imagine if that were happening in a 40-pound return header, not 5 psi, you know, almost a 3-bar header, a 0.3 megapascal header. Just imagine if that is happening, or worse yet, a 1 megapascal, 10-bar, 145 psi header. Just imagine how rapid and violent that could be. That is when flash or live steam collapses in a condensate line. It is collapse hammer, it's steam induced because the steam is the inducer. The steam collapses and creates the hammer. All right, so let's talk, how does steam traps get related to this? Well, we know that if you have a blocked trap, that means the line goes cold, the trap goes cold, and that leads to water hammer and steam mains. That's what we covered in part 1. But now, when you have leaking traps or blowing traps, that pushes steam into the condensate header. Then if steam forms a pocket and that's collapsing, and that forms water hammer and condensate returns, collapse hammer. That's what we're going to study today. What causes it? Well, leaking traps and open bypasses are the biggest cause that you can easily proactively fix. All you have to do is have a sustainable steam trap management program, a good way of identifying the condition of your traps, and a proactive effort, a high priority proactive effort to fix leaking and blowing traps. Now, when you're doing your surveys, you also want to be on the lookout for open bypass valves around equipment, because what that tells you is that the condensate drainage device that's installed on that equipment was not sufficient to work. And probably the operator said, hey, our heat transfer equipment isn't working, I'm going to open the bypass. They might have opened it because they had elevated back pressure for some time, and then they didn't close it off. But whatever, the drainage device is not working, that open bypass is a really high priority to fix, which I'll explain later. Now, you can have flash or bleed steam through, but as long as it's not a lot of steam, it shouldn't be creating a lot of hammer, except flash steam will create hammer when it pockets at the bottom of a vertical riser in transport piping. We'll talk about that later. And the one I really hate to see there is the control valve blow through, because people think that a control valve doesn't blow through steam, but an outlet control valve does blow through steam, or can blow through steam, and I'll show you some examples. Steam-induced hammer, collapse hammer, from blowing traps, open bypasses, control valve blow through, or flash or bleed steam. Typically bottling up at the bottom of a vertical riser. So you want to make sure you have good steam traps and not bad ones. Otherwise, you're going to have problems with equipment. If you want to see the problems and see some historical events, please read that article from 2015 Chemical Engineering. In that article, I talk about this site from 2002 to 2013. They had a gap year where they didn't do testing here in 2004. They had a gap year in 2012. But look at this. Their trap population is going from around 52% good to 38% good. I want you to think about that for a second. The original designers said you need to have 100% of the traps with a reasonable amount of redundancy to have proper operation of your plant. And this plant has decided to allow those traps to go down to 38% good and 62% not good. Do you think that's a relatively safe site? Do you think that site can operate anywhere close to benchmark? I mean, it's like valving out 62% of your traps and not having them there doing their job. But interestingly enough, we're talking about condensate returns today. So here is what we're concerned about. The not in service traps that might have been leaking, and then somebody just valved them out and said they were not in service. Now, they truly might not be in service. We don't know that from this graph. And they've got 2% of traps, 1 or 2% of traps leaking, which is the orange. That's actually pretty good. So this site, because they have so many blue cold failure traps, I would expect to see a lot of hammer on the steam supply and on steam equipment, problems with flares, problems with turbines. But because they only have 2% of the traps leaking, I would not expect to see a lot of problem in the condensate return headers. Now this site we took a look at before, if you looked at part 1, and here from 1997 to 2011, we've got really great data, and look what they're doing. They got rid of these cold failures where they were having a lot of problems. They were knocking out turbines right and left on their 400-pound system. They got rid of these cold traps, and they moved this up to only, 2% cold, 2 or 3% cold. That is awesome. However, we see from this point, 2007 to 2011, they let their leakers rise. Look at that. I would expect that we would start to see some problems in the condensate header with that system, because now you've got 21% of the traps were not in service, might have been blowing, they might have valved them out, but you've got what, about 12% of the traps there that are leaking. That's going to create some problem in the condensate header. So you could be sure of that, unless they're leaking the atmosphere. So in why bad things happen to good steam equipment, I talk about maintaining a good traps threshold. I want people to say, get out of that caution, warning, danger zone and get into the best average good, which is somewhere around 85% of the traps good. If I were talking on steam side, I would say you don't want those cold traps to be going up. You want that number to go down. But we're not talking about the steam side today. We're talking about the condensate side. So I really want to see the energy, the leaking traps go down, because that's what's going to create problems in our condensate headers. I don't want to see leaking and blowing traps into those headers. Okay, I never really quite understand this. I want you to think about this from my perspective for a second. The original designer and licensor of the technology that the site is using, whatever they're producing, they've said, hey guys, you need like 12 or 13,000 traps for your site. And someone said, oh, we don't want to do that. What's the minimum we can get away with? You can get away with 11,000 traps. Okay, well then put 11,000 traps in. So they put 11,000 traps in. Over the time, I don't know what happens. They get into that caution zone, and they usually have some sort of an event at the site which gets everybody all of a sudden to pay attention. Then they call us in and say, hey, we just had an event, can you help us? Well, sure, you're down in that caution warning danger zone. How did you get down here? You're at 64% of your traps good. I never understand that. If you need 11,000 traps close to that functional, why not fight for that budget money to keep the plant working at optimum efficiency and mitigating against these issues before you let them happen? People don't understand when they get down to 7,000 traps. Here we are at 7,000 traps. All of a sudden they have an incident. They say, okay, we're going to get up to 9,000 traps good in 1 year. There's 12 months, we're going to get to 9,000 traps. Look at that. No, not really, because you've got new accumulated failures. It's a mature site. So you get down here to 8,000 traps. Then you try to do the same thing, and you get down, and you try to do the same thing. And by the end of 3 years, you're down to here about 9,000 traps with a highly focused effort. I'm telling you, please read that article, Why Bad Things Happen to Good Steam Equipment. For every year that you have a gap year, that you are not proactively attacking your steam trap population to keep them in good functioning order, it's going to take you about 3 years to get back in shape. And you can't operate at optimal production if you have suboptimal steam quality. Please think about that. "36 months, best sustainable." Now, interestingly enough, people always complain about budget, so I thought I'd better put this MBA to good use. And one day I decided to go and use Excel tables and show them 3 scenarios. Do nothing, do 45% replacements, and do 90% replacements. Why not 100% replacements? Because sometimes you just can't get to all the traps that need to be serviced, okay? I wanted to make it conservative for people. But do you know, if you do a 90% replacement, you get an internal rate of return somewhere around 112%. That's right. Don't shake your head. I mean, you heard right. You get an internal rate of return somewhere around 112%. Where else can you get an IRR based on a 5-year period at 112%? Please read that article to justify why it makes sense to make sure you have the budget money, wherever you get the budget money from, whether it's maintenance budget, wherever, make sure you have the budget money, because you can get an IRR of 112%, all explained in this article. All right, how does live steam enter condensate returns? Well, from blowing traps, but I mean, well, how about this one? This is really neat. I want you to really pay attention to this, and I want you to take a look down there. There's no trap. If you can think of one place in your site right now that has no trap, I want you to write it down, because as soon as you're done with this webinar, you need to go out and figure out how to fix it, and I'm going to show you why. The blow through of this item on 600 psi, 42 bar, 4.2 megapascal could be 6,000 pounds an hour. Now, the pipe size and length actually restricts the flow. If you do a rough calculation of that pipe, it would be, if it's a short distance, it can be over 10,000 pounds an hour. But being conservative, we're going to say the size and length of the pipe is going to restrict the flow like a muffler, let's say. By comparison, at this pressure, a leaking steam trap could leak 40 to 80 pounds an hour. So if we take the average of 60, if you fix that one trap, that's equivalent to fixing the blow through of 100 leaking steam traps at that pressure. Think about how cool that priority is. You can fix 100 traps impact by fixing that one location. I mean, is that cool or what? What did you do today? I fixed 100 traps impact. How'd you do that? 100 traps in one day. Yeah, I just fixed one with no trap. Now, why are bypasses open to bleed live steam into the system? I mean, you got this beautiful 150-pound heater here. You got a trap in the open bypass. Now, it might be a perfectly good trap sitting there. So why did the operator open the bypass? Well, I mean, yes, the trap could be undersized. The heat exchanger could be under a stall condition. The back pressure might have elevated and all of a sudden the trap doesn't work anymore. And yes, the trap might require service. Strainer could be blocked. There could be a lot of reasons, but the operator has opened that bypass. Yeah, well, they always open the bypasses, you might think. Well, they only do it when the drainage device is not working for some reason. But the blow through off of this trap right here, off of this bypass, could be 10,000 pounds an hour. Now, applying the piping is going to restrict that flow, otherwise it could be more. Using the same 60 pounds an hour scenario of the high pressure trap, that's 170 leaking traps. But if you think that a lower pressure trap only leaks 30 pounds an hour, that would be equivalent to 340 leaking traps that could be fixed by addressing that open bypass. I mean, how cool is that? You can fix between 170 and 340 leaking traps for this pressure by addressing one open bypass. Think about that. Traps, lines with no traps on them and open bypasses, that's big, high value, low hanging fruit opportunity. Now I want to talk a little bit about the extended stall chart. I co-invented the stall chart with another gentleman back in the 80s, but I invented the extended stall chart in 2003 and published it in 2004. We're going to use the extended stall chart in a different way right now than what I wrote about in this article. But I'm going to tell you that this next section, whatever you're drinking, a cup of coffee, a glass of water, tea, sit and relax, because this is the most challenging thing to understand in this session. So here we go. Here's the extended stall chart, and I'm going to talk about it just a little bit. Down here, we've got the demand section. You've got to take some product, and you've got to take a mass flow, and you've got to heat it up to a certain off temperature, and there's your mean temperature difference for this flow. You're going to do it through a heat exchanger, and this is your supply side. So your steam is going to start here at the highest temperature and move down. However, when the heat exchanger would get fouled, you wouldn't have 100% surface area anymore. You would have less surface area. So we're going to give it some oversurfacing. In this case, we're going to give it 55% oversurfacing here. Now the steam is going to come in there. I lost my cursor, and it's going to go down this line. All right, now let's take a look at this. We're going to put some back pressure on this system. And if you read over here in the right scale, it's 10 pounds of back pressure. We've got 155% of surface area, so our steam is going to come down this line. And look at that point where their circle comes out. That is where the steam pressure is approximately equal to the back pressure of 10. And if you look down, that happens about 85% of low. So if the steam pressure driving through the heater is the same as the back pressure, you get no flow. It's called the stall point. It stalls. Why? Because the inlet pressure is the same as the back pressure. But you say that's not really going to be a problem because we operate at 95 to 100% of demand all the time. We never have a marketing mix that changes. Well, that's great. That's great to know. Now, as a heat exchanger gets fouled, the effective surface area moves from 55% over towards 100% scale, like I'm doing here with this arrow. When that happens, from Q is UA delta T, since the effective area has gone down, the delta T has to go up, so the steam pressure rises. And there it goes. As the area goes down, the effective area goes down, the steam pressure goes up. Now, we're going to follow this particular curve. And look, the stall point has just jumped down to 55%. It went from 85% to 55%. Why? We have less area, so we've got higher pressure. So we've got a lot of pressure to overcome that 10 pounds of back pressure. But now here's what happens, and it's very confounding for people in the site, and I want you to think about this. They don't have budget money, they have gap years, they wish they could fix the steam traps, they just don't. They didn't pay attention to the open bypass valves, they didn't pay attention to the blowing traps, whatever. And what happens is the back pressure goes from 10 to 20. You see it jump up there to 20? It happens gradually. It could just be 1 or 2 heaters opening up bypass lines if they're large heaters with 2-inch lines. Now what happens to the stall point? Well, the stall point jumps from 55%, going to jump up here. And that's at 65%. You say, that's okay, Jim. We always work at 95% of load. It's no problem. Except for one thing. Now, at some point, you're going to clean or retube that tube bundle. When you do that, now you have 155% of surfacing again. Now your stall point happens over here at 100%. So even when you're at a full load condition, there is no longer enough pressure to get into the back pressure that has been elevated to 20. And people get confounded and say, I don't get it. I took everything apart, it was working fine, I cleaned the tube bundle, I put it back together, and all of a sudden your trap doesn't work. It's not the trap doesn't work. Your pressure dropped because you have more surface area. And you didn't realize it, but over the time your back pressure rose. That's why you have to stay on top of the back pressure. You have to stay on top of the traps all the time, and you have to fix leaking, blowing steam traps, and you have to make sure that you handle the open bypasses. You don't want that back pressure to elevate. It's easy to see where people are having problems. This is what I call the double whammy right here. So I come into a reboiler and I take a look and I see, well, look what's happening there with that collar. I immediately know if they got a leak collar like that, that means they have a problem. And they've got a stratified heater, and that's because they have stall or cold trap failure. And you're like, wait a minute, Jim, that's a stall or a cold trap failure. That happens on a steam line. Sure it does. And then you're going to have steam bubbles go into that thing, and the steam is going to collapse, and you're going to hammer the tubes, and you're going to hammer the channel head gasket. Why are you talking about that on your condensate line? Because when that happens, they're also going to open the bypass, and that's the double whammy. They get hammer on the inlet side, and they get steam going into the header on the outlet side. It's the double whammy situation. So when you see this in the plant, when you walk through the plant and you see a leak collar, and you know you got stratification on your heater, that is something that is a high value opportunity to fix, because that is a double whammy. Now we're going to talk about outlet control valves used as steam traps. Sometimes when a plant gets built, the designer will put in an outlet control valve. If you've noticed, I've got process fluid in here. I've got no control valve on the inlet side. I've got no trap on the outlet side. Why? Because I got a control valve. There's no inlet control valve and there's no trap on the outlet. I just have a small control valve, because if I had done this with a control valve in the inlet, it would probably be bigger. It might be like a 3 or 4 inch control valve in the inlet and like a 3-inch trap on the outlet, or a 2-inch trap on the outlet. But now what I've done is I've gotten rid of that 3 or 4 inch inlet control valve, and I've just put like a 2-inch condensate outlet valve. I get rid of the 3 or 2-inch trap on the outlet side, and I save myself some money on a capital cost. Hey, that's okay. I don't have to operate the plant. I just have to build it. That's really tough, because what happens is you got to ask yourself, does that control valve blow through? Well, no, it's supposed to keep a water level like I see here, Jim. Well, you mean it doesn't ever get dry like that? No, it never gets dry like that. Well, why is it that we see blow through as common through this type of a setup? And that causes erosion of piping and the loss of duty of the exchanger, and it causes hammering. Well, I'd like to see pictures of that. Okay, well, wait a minute. What about if I put a level pot in there? You see the level transmitter there? You know, this is the way that works. When it goes down, it shuts off so I don't blow through. When it goes up, it opens up and it gets the condensate out, or some modulation in between that. And that there's no way that can blow steam. That's going to maintain a level pot. Oh, really? Does it always maintain a condensate seal? Or is there an override in this controller that you can override for production if you're off spec on your production or off target? And then you drain the level pot dry and you got a lot of blow through. And you say, that just can't happen. I'd like to see pictures of that. Well, I'm glad you asked. Here's a depropanizer reboiler, and you got some steam blowing through right here. And you got some steam blowing through right here in this outlet control valve. Why is that? I'll tell you why. It's because the pipe's eroded and it's leaking. But in addition to that, the outlet valves in both cases were open 100%, and there was zero condensate in the pot level. I want you to think for a second. Take a guess. How much steam is blowing into the return header? Or how about this regen reboiler? There's the condensate pot, and you can see the control valve. Nice looking setup. Looks pretty clean on the outside, but the average blow through of this was between 3,000 and 5,000 pounds an hour, somewhere between 70 and 140 leaking drip traps. One outlet valve. This is a debutanizer, so this is kind of fun. I mean, the reboiler is flooded, and you take a look over here. Look what you're seeing here. You see a leak collar, and then, you know, look at the temperature stratification. You got 181 degrees stratification from the inlet to outlet. So this thing is flooded. It could be easily fixed with a simple setup like this, which would improve the reliability. It would look something like that, or like that. Just depends on where, you know, put the pump set. One of the guys that's the Steam collaborators today, one of the refineries had a very tough, tight spot. So Justin McFarland, he put this custom system in for there where he went out and measured everything so it fit in a tight space for them. But you can fix these sort of issues. You don't have to have this problem with your channel heads and your reboilers and all that blow through into the return header. And that's a pretty simple fix. Look at that. That's not a lot of pipe and pumps. It's 2 pumps and a little reservoir tank. All right, so here's a 600-pound wax heater. As the pressure goes up, it gets a little more interesting. If you're a process engineer, you're looking at this and you're looking at that black line and you say, I am charting the heck out of that product. That's 1 year data, and I'm probably not paying that much attention to this bottom part of the graph, which is the condensate level with the black line. And we need to take a look at that black line there, because they're the condensate level 0 and they're the condensate level 0. And if you add all that up, it's multiple extended blow-through periods. And the 600-pound blow-through of this was 3,300 pounds an hour, which is equal to 55 leaking traps. But the peak blow-through was 10,000 pounds an hour. Now, that's 220 leaking traps. Do you think that peak blow-through elevated the back pressure in that return header to the point where somebody else opened up a bypass valve? Here's a dewaxed oil heater. Same sort of deal, 1 year data. Look at all the multiple spots where the condensate had 0 level, including a 3-month blow-through period. So that was 8,400 pounds an hour blow-through for the year. Imagine that, 8,400 pounds an hour, 8,000 pounds of steam an hour, whatever your price of 1,000 pounds of steam is for, over 8,000 hours of operation, equal to 140 steam traps. But the peak, look at that, 28,000 pounds an hour. It's like going out in the system and having an operator open 470 traps at one time into the return header. Can you imagine? Do you think that elevated the return header pressure? And that's why I'm not in love with outlet control valves, and I think you should get a better system to fix it. A better system might look something like this, where we put a trap set in there, and it might have to go to a vented receiver, and yes, you might have to do something with that vent. You might use a pinch analysis sort of idea and try to use that to heat some of the cold stream. You might condense it or something like that, and then you just pump it away. But there's your simple pump set to pump it away, right there. It's not a bad situation to do that. It's a lot better than blowing 28,000 pounds an hour of steam into your return header and creating all that back pressure and all that hammering and damage to the piping system. All right, flash steam, how does it affect condensate returns? So there's your steam trap on the left and the orifice is circled. And now you see when condensate goes from a high pressure region to a low pressure region, it flashes. That's generated with a large pressure drop. So most people don't realize it. This is one of the phenomena of steam, that when you go through a trap and you get flash steam, the pipe is mostly filled with steam, not with condensate. It's hard for people to take a look that the pipe volume is like that graphic on the left right over here. They don't really notice that. They think, oh, really, I thought it's like water. No, you can calculate it. You can take the sensible heat or enthalpy of the high pressure minus the enthalpy of the low pressure, divided by the enthalpy of the low pressure, using that formula. And times 100, you get the percent of flash. So if we do calculations, you can go to engineering calculator, like I said before, or engineering toolbox on your iPhone, and you can put the units in and you can calculate it. But I've done it here for you. So here is 650 to 60 psi. Let's take a look at the mass volume flash analysis. Well, that's not bad. Look at that. 77% of it is condensate and 23% of it is steam. Jim, I thought you told me it's mostly full of steam. That's like, it's not, it's like a quarter steam. Yeah, maybe if you're talking about mass. But when you put the specific volume to it and do the mass volume analysis, it's 99% proportioned by steam. Wow, isn't that shocking? Well, yeah, but 650 to 60, we don't often do that, Jim. I mean, normally we're like 150 to 30. Okay, well, there's 150 to 30 for you. It's 98% full of flash steam. And if you go 150 to a flash vessel to 0, it's 99% full of steam. Either way you deal with it, when you're coming out of a piece of steam equipment or a steam trap and you're going to a lower pressure, you've got to deal with the flash effect. Okay, so we can calculate flash steam from a table. And here you see at 0 pounds, it's 16.1% flash. So the higher the delta P, from 145 to 0, from 10 bar, 1 megapascal to 0, okay, you're going to get a high percentage of flash, and in example 1, that's 16.1% flash. Let's take a look at example 2. That volume was 300 to 1 steam, by the way. That's 44 psi. So, just a little bit like around 3 bar. Well, that's 8.2% flash. That's like half. So what is it, like 150 to 1? No, 8.2% flash has a different specific volume. It's 32 to 1. So it's 1/10. That's one of the reasons why people get a lot of pressure in their return header. It's compressing the steam. So you take a look here, and there's 145 to 0, and there's 145 to 44. It's almost a 10 to 1 ratio. Take a look at that. A lot of the topics we're talking about today are covered in this article I did called Stop Knocking Your Condensate Return. It's one of the attachments and handouts for this, so you can download it if you'd like to see that. If not, it's on the steam theory section of TLV.com. We want to mitigate water hammer at a flash drum. So if you've got like different pressure streams coming into a flash drum, or you've got a low line stream coming in, if that steam go mix with the water where the condensate is coming in, that condensate coming in could be relatively cold, and it will collapse that steam. So when you get the backflow, it's going to collapse it and you get a hammer. You get pocketing at a riser. Here's a riser, and the steam pocket, that when you get that water displaced by steam, that water doesn't want to rise until you close off that section right here. And that creates a hammer with the steam pocket. So here is a place in Africa. They had a little problem with this 5 meter high, 5 or 5.5 meter high flash drum. They had a lot of pocketing. They were blowing apart the valve at the top. They were damaging the flange. Here's another flash vessel issue that can happen if you're on a design group or an EPC. Whoever in the equipment group or whoever is designing your flash vessel, make sure they consider the amount of flash, because this particular one, which was also about 5 meters high, had a 3-inch flange on it because they thought that's all that was necessary. However, the actual line, because of flash steam, was like an 8 or 10-inch line. So they had to neck it down to get into the flash drum. Yes, they were blowing apart the gaskets here. They were blowing apart this flange. It was quite a problem. And the solution is to make sure that you have the same size going in. So the two groups definitely have to know and estimate the amount of flash when they size the vessels to make sure the vessels have a big enough pipe. When you're getting a vessel that's 5 meters tall, 15, 16, 17 feet high, it isn't that much of a difference in cost to put in a bigger than you expect outlet. You can always neck up to it, but you don't want to neck down to it. You know, it's nice when we can just get all the condensate coming in, no backflows, and just get everything coming out the top properly. If you can't get everything coming out the top properly and with low velocity, if you get high velocity coming out the top here because this is too small, well, then that creates a pressure in the system. And the pressure in the system elevates the condensate temperature. That means your pump set that is taking that condensate is hotter temperature than it should be. The vapor pressure is higher, and that means that that is going to turn into steam as soon as you get a dynamic change. So when you spin that impeller, the velocity goes up, the dynamic goes up, the static pressure goes down, and you get a collapse. Sorry, you get an expansion of some of the water droplets in the vapor because of the drop in pressure. But because there's water all around it, the water is a heat sink, and it actually causes those steam that just expanded, it causes those droplets to go back down and form water again. You call that cavitation. That's why the impellers look like that, or we have different blades pulled off, different vanes pulled off of an impeller. That's really what they look like. They don't always look pretty like that one. They look more like this one. We like to stop that stuff from happening, mitigate impeller damage. It starts with good flashing, with good venting, and get that temperature down low where you need that temperature to be relative to the NPSH required for the pump. Condensate system. So hydrocarbon processing last year, this is part 2. Part 1 is really a parallel to what I did on the water hammer side last week. Part 2 is relative to this one. You could read that if you wanted to. We're going to talk about flashing condensate, especially in vertical condensate returns. This is a refinery somewhere in the Gulf Coast, you know, somewhere between, let's say, Florida, Mississippi, and Texas. So sometimes I wonder when you have expansion loops, like, do people think that the line in a condensate return is full of condensate the way this pretty graphic shows? I mean, because I'll tell you, it's not. What do you think that line normally looks like? At least for some portion of it, it's mostly full of steam. Now, if you notice, there's a little bit of water down there. How does that water jump up? It can't jump up in that expansion loop. And now you've got the water to this level. Well, that can't jump up either. So, you know, if you have a long distance, like there was a place in Africa that had, you know, 500 feet difference, you know, 160 meters, something like that, 170 meters. And they were getting sloshing back and forth in that line with the steam pockets collapsing. And it was creating a lot of hammer. It was at like a a little more like 10, 11 bar system. So they were actually blowing valves off the line. Can you imagine? They're blowing valves like 10, 15 meters off the line. So if you get the line to close off like this, now you're going to propel a slug upwards into that expansion loop. And that's going to cause erosion, and it's going to cause leaks, and it could cause quite a lot of hammer. And there you go. Just imagine that slug getting propelled now by flash steam downstream. So this refinery site that we talked about, they had 6 leaks. If you look there, there's 5. That's because they had another leak 6 to the left of the line. That's where the leaks were. So here they got back slams because the pocket was reversing. The pocket would collapse right here, and then you would send a force vector back. So they were getting a blowout there. They were shooting, when the condensate would seal off the elbow, would shoot upwards and cause a blowout up there. Then the condensate would cause a blowout when it hit that part right up here. Then it would come down at high velocity from the acceleration of gravity, cause a blowout here, cause a blowout down here. And here it would rocket back and forth when it collapsed and send shock waves back and forth. So it had a blowout here, and yes, a blowout here. 6 leaks, and the problem with this line was most of the line was up in the 3rd rack. So they couldn't actually get to fix it. So as you walk through the refinery, they had a lot of it taped off. So for a site, a couple of sites, I came up with this idea of a drop-down loop seal. It's not a substitute for proper gravity return. It really came from a thought process where you take a look at, sulfur in pits, and you got the coils in pits, and they have lift fittings that get the condensate out of the coils. And even in tanks like chromium tanks, you got lift fittings with a pipe within a pipe to get it elevated. Well, I thought you're not going to put a pipe within a pipe in, a 6-inch header or a 4-inch header or something like that, or an 8-inch header. So, but what about a drop-down loop seal using all long radius elbows in here for a nice smooth flow? So here's a concept of a drop-down loop seal. It's to mitigate against the collapse of the pocket at the riser and sloshing and surging back along the line, because you get the collapse at the riser itself because there's a wall, a vertical wall, and you have to close that off, and you get the collapse of the steam pocket. But back in the line, you get some sloshing and some surging going on, and you get all along the line, depending on how far along the line is in the horizontal, you get a lot of sloshing and surging, and you get collapse there. So the drop-down loop seal is a concept only. And, if you wanted to do this or take a look at doing this in your site, you must get the design made by a professional engineer that has experience in fluid dynamics and stress analysis. This is just a concept. Every system is unique. You need a professional engineer to design this system for you relative to your system and determine if it'll work. And it has to be an engineer experienced in fluid dynamics and stress analysis. We don't want to create any issues for anyone. So get that done by a proper engineer for your site. The whole concept here is to use long radius elbows and a nice sweep. Put a check valve low. And because you've got a check valve there, that check valve is going to get a lot of hammering from back slams because collapse of condensate in that line. So you're going to want to change that check valve without dumping the condensate. So it's going to need a bypass of some design, not a triangulated bypass, but that's just make room on the drawing. But you need a bypass of some design, also designed by the engineer, so you can valve out the check valve and replace the check valve while you're keeping your condensate flowing. And isolation valves have to be full pore, so you don't have any restrictions in there. Excuse me. So on the refinery in Texas, that would look something like this, where they were told to get a professional engineer to design it for them, DDLS1, DDLS2, and DDLS3. All long radius elbows. So I thought it would be interesting, and some of the guys that are on today, Andrew Moore and Justin McFarland, and some other of our engineers came up with this. They decided to do this in our lab to see what it would look like. So here you've got the top pipe. Now it's a short distance of pipe. What is it, 10 feet? Not even. And we've got very low air pressure in here, so you're going to have an aerodynamic property the air will not collapse the way steam would collapse. So it's not the same as thermodynamic. But even so, take a look at this water and watch for the slugs. Here it comes. Bam. Let's take a little closer look. Bam. And you see how it gets moved upwards. You've got two phases that are pretty separate. You've got a closed off slug, and then you've got a slosh slurry going upwards. So let's take a look with the drop-down loop seal. Now here, because of acrylic piping, we couldn't get long radius elbows. We put a horizontal section in here so you can see the interface, but all of this should be long radius elbows. Take a look along here, how smooth this flow is, and you don't get the wave action going back and forth. It almost doesn't even look like it's working. You can see it here, it's working, but you don't see anything here. Look at that. Let's look a little closer. You see the interface. Let's look a little closer. Right in there. So what you've done is mitigated the surging and the sloshing back and forth that pipe. And let's take a closer look at the elbow. Again, it would be a long radius elbow. You're not getting the same hammer effect that you had before. And let's go down to the interface, and you can see why this should be long radius elbows when you take a look at the interface. You are see a lot of action at the interface, which is why you want an engineer experienced in fluid dynamics and stress analysis to be able to make sure that that part of it is designed properly. You don't want to have any problem there where that arrow's pointing. So a drop-down loop seal is an idea that you may use. You could always just vent it off and flash it and pump it overhead if you wanted to get rid of a water hammer, which would be safe. And you could always elevate the line. The elevated line is what would be the perfect solution. We have everything with a gravity return. It's just that people don't often have that. It's unfortunate. So we've got to deal with something and mitigate against it in a safe way. So we see a lot of vertical risers, and we see all this pocketing happening here, just like what we showed you. So a drop-down loop seal might help that. Here you've got a cold stream coming in, a flashing stream coming in, mixing. You're going to have a lot of hammer. So one of my friends out in the Middle East had this problem, a process engineer, and said, I've got these streams mixing. I've got a line like this. It's like a 130 C temperature. And I've got a cold stream coming in, and it creates a problem. So here it is. Here's the problem. Here's this thermocycline reboiler that this engineer had, 3.7 bar steam coming into the reboiler. The reboiler was designed and built like 10 years before, and it was way over-surfaced. So what happens is they had way more surface area than they needed. The condensate level was really low. Your back pressure over here to the right is 1.8 bar. And it's hot flashing condensate around 130 C. And here you've got an oversurface low pressure heater, which only has 0.35 bar in that heater, that reboiler. So down there, your pressure differential from 0.35 bar through that control valve to the outlet line is a minus 1.45 bar G. There's no way that's going to flow. So guess what happens to the condensate? It's insufficient pressure. So guess what they did with the condensate? Can you figure it out? You know it. They wasted it to grade. But in the Middle East, condensate is so valuable. Water is so valuable. They hate dumping that to grade. So they said, wait a minute, let's do something else. So my process engineer friend said, what about putting the level controller, the level transmitter high, rather, and you see there, we're going to flood this reboiler. So they flooded the reboiler. They had only one tapping on the reboiler, so they didn't have any choice where they could do it. They did it right there. That gave them 2.2 bar steam pressure. That was pretty cool because now you got a plus 0.4 bar G differential against the outlet back pressure. But that's sufficient pressure, but it's a high resonance time in that thermosiphon reboiler. So what do you think is happening to the temperature of the condensate? It's getting colder. In fact, it reached equilibrium with the process. So now you take a cold condensate stream of 94C and you put that cold condensate into that hot flashing condensate line into the top where the cold condensate is going to hit the flash steam moving across the top. What do you think is going to happen? There you go. Bam. That's what happened. What do you think is going to happen? That's what happens right there. So what do you think they had to do? Yep, they had to waste that condensate. And then the problem with it is they were really close to the flood line in that thermosiphon reboiler entry point. So they had all kinds of problems with that. So my friend said, what should I do? And I said, well, that's pretty simple. Just put in a power trap, a simple little power trap. You can take the 3.7 bar G to motivate it. Use a little 8-inch pipe for the reservoir. Everything's fine. One of the collaborators today, Justin McFarland, drew that system out for me. And there you go. Now, this temperature, depending on what the temperature of the condensate is, notice they're happy now, right? This is a happy face. But it depends on the temperature of the condensate coming into that line. If the temperature coming out of that is still going to be close to like 94C or something like that, or maybe like close to 100C, I might put the entry point here into the side rather than the top. Because the side, it'll hit the liquid condensate, and I wouldn't bullhead it in at 90 degrees. I'd come into it here at a 45 degree and let the flow go in the direction of the flow. And that way you're less likely to get a collapse from swelling of condensate there if you bullhead it. And when you come into the top, you're immediately mixing the colder condensate with the flash steam. You're going to get a collapse. You put it into the side as 90 degree, you're going to get a bullhead. You're going to get a swell of condensate. You're going to get a collapse. So I'd put it in there at a 45 degree angle from the side and see if that worked. And if you had the line down to make that entry point, it's not a lot of condensate. I mean, a couple thousand pounds. What you could do is you could put 3 or 4 entry points of small bore diameter, 5-10 feet apart. So you're mixing the condensate from this line into that line at several locations along the line. You'll get it in there because you put blow valves in there to adjust how it goes into that flow, and that would mitigate the hammer, and that would save you installing 800, 1,000 feet of 2-inch pipeline. And that's really the goal, to recover the condensate and not have to install 800 to 1,000 feet of pipe. So that installation looks like that. It was 8-inch diameter pipe that was 1.5 feet long. Not a big thing, right? Right off of here, 2-inch pipe right into the reservoir, into the power trap, out the go. A nice little drawing. It looks just like that. Isn't that a whole lot better than installing approximately 900 feet of 2 or 3-inch pipe? Flooded returns. So we just wish all the systems flowed so nicely like this. We never go into a pumped return. We never discharge into a pump return. We don't put cold condensate into a 2-phase return. If only it works that way. But people have flooded returns and they put in, in a cold return, they put in 2-phase flow and they get hammered from the collapse. That's steam-induced hammer or collapse hammer. But they also do this. They got a flashing line. Now take a look what happens if you put a top entry point with cold condensate into a flashing line. You can get a backflow of steam. And now that steam is going to get collapsed by the cold condensate. You're going to hammer in that line. So what we would do is put a check valve in there. But not any check valve. We put not a swing type check valve, because look what happens. The steam can flow around it. It might be mitigated if you have a spring-loaded swing check valve, but the better way to do is like a spring-loaded disc valve, a disc check, not a swing check. So here is flash steam going into a single-phase cold return out of this equipment. That's just asking for trouble. That is never going to work right. You cannot take the discharge from steam equipment into a pumped cold return. You get collapse hammer. Same problem here. Now, you say, well, what do I do if I got this hot flashing condensate? If it's not a lot, you can put a sparge pipe. And sometimes sparging it in with smaller holes will dissipate it enough. You put a larger section of pipe, you put a sparge pipe in there, and the larger section will dissipate it. And that will help you avoid having to put in 100 or a couple hundred feet of separate line. All right, well, I hope that these little tips helped in some way. Just understand there are ways to deal with things. Just talk to us or the vendor that you use at your site. Steam is an asset. Its quality definitely impacts production. You cannot produce optimal production with suboptimal steam. However, condensate is also an asset, and its quality also impacts production, particularly when you have pressurized return lines that push back on the output of every single heat transfer equipment on your site. So if you want to have peace of mind, one of the best things you can do is maintain a good traps threshold above 85% of your traps good at all times. You can do that using the TrapMan system. If you want to learn more about that, one of our Steam collaborators today, John Walter, wrote this incredible article, Implement a Sustainable Steam Trap Management Program. Please download it and read it. It's one of the handouts with the session. We're TLV. We've been in business since 1950. On May 18th, we celebrated our 70th year in business. We're an ASMEN and NPT manufacturer, which means that we've been making nuclear products. Actually, we've been making nuclear products for over 50 years. That's the level of quality. We have a lot of certifications. We started in Japan in 1950 over here. This webinar is coming to you from the other side of the world, Charlotte, North Carolina. Thank you very much for attending the webinar. And that concludes my webinar on mitigating water hammer and steam and condensate systems, particularly condensates. Thank you. And now I open this up for question and answer, and I'm going to ask the Steam collaborators to turn their cameras on.
All right, Jim. Well, thanks a lot. I mean, that is an awesome presentation. There's a tremendous amount of information there. I think that everybody kind of intuitively understands water hammer on the steam system side, but I think the condensate system side is often not understood. So thank you for reviewing the so many different ways that we can kind of get into trouble and the sources of water hammer. And I think particularly for me, one of the I guess the powerful lessons in there is dealing with our heat transfer processes and outlet control. And we always talk about the difficulty of outlet control as far as response times and things like that. But wow, you know, those examples that you gave in terms of extended periods of blow through and what that's doing to our condensate return system, that's that made a point. So anyway, thank you very much for identifying all these experiences that we've got and sharing them with everyone today. So we had a couple of questions that I want to bring back to the team today, and several questions about check valves. And Jim addressed check valves in a couple of places throughout today's presentation, but I'm still going to kick it back to Justin McFarland. If he could do a little bit of a summary. We had some questions about where and when to utilize check valves on the outlets of steam traps and also in the condensate return lines to mitigate water hammer. So Justin?
Sure, thanks Norm. Well, we definitely recommend steam traps, or excuse me, check valves on the discharge side of steam traps. It's not absolutely necessary for traps that are discharging to atmosphere with no lift after that, but there are some precautions to take if it's discharging to a pool that could flood, for example. You could suction water after the system shuts down. But definitely on pressurized return systems after check valves. Sometimes, depending on the application, we would even recommend to have a check valve on the line before it discharges into the main return, so immediately before it ties in there. On main return lines, before a lift, immediately before that lift, or even on that lift is a good location for a check valve. And as you saw in Jim's illustrations, when using the drop-down loop seal, hopefully you noticed a check valve on the vertical portion of it, that DDLS designed to help prevent backflow and to help minimize any effects of sloshing and to help mitigate that water hammer issue.
Thank you, Justin. Thank you for that summary. That was great. We got another question asking us to comment on the practice of utilizing or blanketing the condensate return lines with nitrogen as a way to help lessen or mitigate against water hammer. So I want to pass that one over to Andrew Moore. Drew, could you address that for us?
Yeah, so this is a practice that we have seen, and it is a little bit controversial, I guess you could say. So the idea is injecting nitrogen directly into your condensate return line. And the idea there is that the nitrogen will cushion the collapse of any steam pockets in your condensate return line. Now, this is really an expensive Band-Aid to a problem rather than really a solution. You're addressing the symptoms rather than what's really causing the water hammer, which is usually leaking steam traps, open bypasses, or an incorrectly designed system. On top of all of that, injecting nitrogen is also going to increase your back pressure in your condensate return line, which can also have some adverse consequences.
Okay, thank you, Drew. I think that's an important comment. We see that sometimes in different plants. And again, I think the key thing is getting back to the root cause. Let's try to address the problem at its source. So thank you for that. So that's really all we have time for today as far as general Q&A. We have been responding to your individual questions as they've come in, and any that we have missed, please be patient. We'll be getting back to you after today's webinar individually to write to you, maybe to confirm some of the details in your application and issues, and you know, to try to wrap up and address your questions. So anyway, thank you for your questions and contributing to the program today. And with that, Jim, I'll kick it back to you to wrap things up.
Thank you very much, Norm. Well, everyone, I just want to say again, thank you, as everyone else has said. We're STEAM people. We love STEAM and we love solving problems. So please call us anytime that you would like. Have a great day. Thanks, everyone. Bye-bye.
Thank you.